双语音标领航，注音阅读启蒙，叶兴阳有声读物。
Great Astronomers by R.S. Ball. Preface. It has been my object in these pages to present the life of each astronomer in such detail as to enable the reader to realize in some degree the man's character and surroundings. And I have endeavored to indicate as clearly as circumstances would permit the main features of the discoveries by which he has become known. There are many types of astronomers, from the stargazer, who merely watches the heavens, to the abstract mathematician who merely works at his desk. It has, consequently, been necessary in the case of some lives to adopt a very different treatment from that which seemed suitable for others. While the work was in progress, some of the sketches appeared in Good Words. The chapter on Brinkley has been chiefly derived from an article on the history of Dunsink Observatory, which was published on the occasion of the tercentenary celebration of the University of Dublin in 1892. And the life of Sir William Rowan Hamilton is taken, with a few alterations and omissions, from an article contributed to the Quarterly Review on Graves' life of the great mathematician. The remaining chapters now appear for the first time, for many of the facts contained in the sketch of the late Professor Adams. I am indebted to the obituary notice written by my friend Dr. J.W.L. Glaisher for the Royal Astronomical Society, while with regard to the late Sir George Airy, I have a similar acknowledgment to make to Professor H.H. Turner. To my friend Dr. Arthur A. Rambot I owe my hearty thanks for his kindness in aiding me in the revision of the work. R.S.B. The Observatory, Cambridge, October, 1895. Contents. Introduction. Ptolemy. Copernicus. Tycho Brahe. Galileo. Kepler. Isaac Newton. Flamsteed. Halley. Bradley. William Herschel. Laplace. Brinkley. John Herschel. The Earl of Rosse. Airy. Hamilton. Leverrier. Adams. List of illustrations. The Observatory. Greenwich. Ptolemy. Ptolemy's planetary scheme. Ptolemy's theory of the movement of Mars. Thorne. From an old print. Copernicus. Frauenberg. From an old print. Explanation of planetary movements. Tycho Brahe. Tycho's cross staff. Tycho's new star sextant of 1572. Tycho's trigonic sextant. Tycho's astronomic sextant. Tycho's equatorial armillary. The Great Augsburg Quadrant. Tycho's new scheme of the terrestrial system. 1577. Uraniborg and its grounds. Ground plan of the observatory. The Observatory of Uraniborg. Island of Hvn. Effigy on Tycho's tomb at Prague. By permission of Messrs. A. and C. Black. Tycho's mural quadrant. Uraniborg. Galileo's pendulum. Galileo. The Villa Arcetri. Facsimile sketch of lunar surface by Galileo. Crest of Galileo's family. Kepler's system of regular solids. Kepler. Symbolical representation of the planetary system. The commemoration of the Rudolphine tables. Woolsthorpe Manor. Trinity College. Cambridge. Diagram of a sunbeam. Isaac Newton. Sir Isaac Newton's little reflector. Sir Isaac Newton's sundial. Sir Isaac Newton's telescope. Sir Isaac Newton's astrolabe. Sir Isaac Newton's sundial in the Royal Society. Flamsteed's house. Flamsteed. Halley. Greenwich Observatory in Halley's time. 7. New King Street. Bath. From a photograph by John Poole. Bath. William Herschel. Caroline Herschel. Street view. Herschel House. Slough. From a photograph by Hill and Saunders. Eden. Garden view. Herschel House. Slough. From a photograph by Hill and Saunders. Eden. Observatory. Herschel House. Slough. From a photograph by Hill and Saunders. Eden. The 40-foot telescope. Herschel House. Slough. From a photograph by Hill and Saunders. Eden. Laplace. The Observatory. Dunsink. From a photograph by W. Lawrence. Dublin. Astronometer made by Sir John Herschel. Sir John Herschel. Nebula in Southern Hemisphere. The Cluster in the Centaur. Observatory at Feldhausen. Granite Column at Feldhausen. The Earl of Ross. Bear Castle. From a photograph by W. Lawrence. Dublin. The Mall. Parsonstown. From a photograph by W. Lawrence. Dublin. Lord Ross's Telescope. From a photograph by W. Lawrence. Dublin. Roman Catholic Church. Parsonstown. From a photograph by W. Lawrence. Dublin. Airy. From a photograph by E. P. Adams. Greenwich. Hamilton. Adams. The Observatory. Cambridge. Introduction. Of all the natural sciences, there is not one which offers such sublime objects to the attention of the inquirer as does the science of astronomy. From the earliest ages, the study of the stars has exercised the same fascination as it possesses at the present day. Among the most primitive peoples, the movements of the sun, the moon, and the stars commanded attention from their supposed influence on human affairs. The practical utilities of astronomy were also obvious in primeval times. Maxims of extreme antiquity show how the avocations of the husbandman are to be guided by the movements of the heavenly bodies. The positions of the stars indicated the time to plow and the time to sow. To the mariner who is seeking a way across the trackless ocean, the heavenly bodies offered the only reliable marks by which his path could be guided. There was, accordingly, a stimulus both from intellectual curiosity and from practical necessity to follow the movements of the stars. Thus began a search for the causes of the ever-varying phenomena which the heavens display. Many of the earliest discoveries are indeed prehistoric. The great diurnal movement of the heavens and the annual revolution of the sun seem to have been known in times far more ancient than those to which any human monuments can be referred. The acuteness of the early observers enabled them to single out the more important of the wanderers which we now call planets. They saw that the star-like objects, Jupiter, Saturn, and Mars, with the more conspicuous Venus, constituted a class of bodies wholly distinct from the fixed stars among which their movements lay, and to which they bear such a superficial resemblance. But the penetration of the early astronomers went even further, for they recognized that Mercury also belongs to the same group, though this particular object is seen so rarely. It would seem that eclipses and other phenomena were observed at Babylon from a very remote period, while the most ancient records of celestial observations that we possess are to be found in the Chinese annals. The study of astronomy, in the sense in which we understand the word, may be said to have commenced under the reign of the Ptolemies at Alexandria. The most famous name in the science of this period is that of Hipparchus, who lived and worked at Rhodes about the year 160 BC. It was his splendid investigations that first wrought the observed facts into a coherent branch of knowledge. He recognized the primary obligation which lies on the student of the heavens to compile as complete an inventory as possible of the objects which are there to be found. Hipparchus accordingly commenced by undertaking, on a small scale, a task exactly similar to that on which modern astronomers, with all available appliances of meridian circles and photographic telescopes, are constantly engaged at the present day. He compiled a catalogue of the principal fixed stars, which is of special value to astronomers, as being the earliest work of its kind which has been handed down. He also studied the movements of the sun and the moon, and framed theories to account for the incessant changes which he saw in progress. He found a much more difficult problem in his attempt to interpret satisfactorily the complicated movements of the planets. With the view of constructing a theory which should give some coherent account of the subject, he made many observations of the places of these wandering stars. How great were the advances which Hipparchus accomplished may be appreciated if we reflect that, as a preliminary task to his more purely astronomical labors, he had to invent that branch of mathematical science by which alone the problems he proposed could be solved. It was for this purpose that he devised the indispensable method of calculation, which we now know so well as trigonometry. Without the aid rendered by this beautiful art, it would have been impossible for any really important advance in astronomical calculation to have been effected. But the discovery which shows, beyond all others, That Hipparchus possessed one of the masterminds of all time was the detection of that remarkable celestial movement known as the precession of the equinoxes. The inquiry which conducted to this discovery involved a most profound investigation, especially when it is remembered that in the days of Hipparchus the means of observation of the heavenly bodies were only of the rudest description, and the available observations of earlier dates were extremely scanty. We can but look with astonishment on the genius of the man who, in spite of such difficulties, was able to detect such a phenomenon as the precession, and to exhibit its actual magnitude. I shall endeavor to explain the nature of this singular celestial movement, for it may be said to offer the first instance in the history of science, in which we find that combination of accurate observation with skillful interpretation, of which, in the subsequent development of astronomy, we have so many splendid examples. The word equinox implies the condition that the night is equal to the day. To a resident on the equator, the night is no doubt equal to the day at all times in the year. But to one who lives on any other part of the earth, in either hemisphere, the night and the day are not generally equal. There is, however, one occasion in spring and another in autumn, on which the day and the night are each 12 hours at all places on the earth. When the night and day are equal in spring, the point which the sun occupies on the heavens is termed the vernal equinox. There is similarly another point in which the sun is situated at the time of the autumnal equinox. In any investigation of the celestial movements, the positions of these two equinoxes on the heavens are of primary importance. And Hipparchus, with the instinct of genius, perceived their significance and commenced to study them. It will be understood that we can always define the position of a point on the sky with reference to the surrounding stars. No doubt we do not see the stars near the sun when the sun is shining, but they are there nevertheless. The ingenuity of Hipparchus enabled him to determine the positions of each of the two equinoxes relatively to the stars which lie in its immediate vicinity. After examination of the celestial places of these points at different periods, he was led to the conclusion that each equinox was moving relatively to the stars, though that movement was so slow that 25,000 years would necessarily elapse before a complete circuit of the heavens was accomplished. Hipparchus traced out this phenomenon and established it on an impregnable basis, so that all astronomers have ever since recognized the precession of the equinoxes as one of the fundamental facts of astronomy. Not until nearly 2,000 years after Hipparchus had made this splendid discovery was the explanation of its cause given by Newton. From the days of Hipparchus down to the present hour, the science of astronomy has steadily grown. One great observer after another has appeared from time to time to reveal some new phenomenon with regard to the celestial bodies or their movements, while from time to time one commanding intellect after another has arisen to explain the true import of the facts of observations. The history of astronomy thus becomes inseparable from the history of the great men to whose labors its development is due. In the ensuing chapters we have endeavored to sketch the lives and the work of the great philosophers, by whose labors the science of astronomy has been created. We shall commence with Ptolemy, who, after the foundations of the science had been laid by Hipparchus, gave to astronomy the form in which it was taught throughout the Middle Ages. We shall next see the mighty revolution in our conceptions of the universe, which are associated with the name of Copernicus. We then pass to those periods illumined by the genius of Galileo and Newton, and afterwards we shall trace the careers of other more recent discoverers, by whose industry and genius the boundaries of human knowledge have been so greatly extended. Our history will be brought down late enough to include some of the illustrious astronomers who labored in the generation which has just passed away. Ptolemy. Plate. Ptolemy. The career of the famous man whose name stands at the head of this chapter is one of the most remarkable in the history of human learning. There may have been other discoverers who have done more for science than ever Ptolemy accomplished, but there never has been any other discoverer whose authority on the subject of the movements of the heavenly bodies has held sway over the minds of men for so long a period as the 14 centuries during which his opinions reigned supreme. The doctrines he laid down in his famous book, the Almagest, prevailed throughout those ages. No substantial addition was made in all that time to the undoubted truths which this work contained. No important correction was made of the serious errors with which Ptolemy's theories were contaminated. The authority of Ptolemy as to all things in the heavens, and as to a good many things on the earth, for the same illustrious man was also a diligent geographer, was invariably final. Though every child may now know more of the actual truths of the celestial motions than ever Ptolemy knew, yet the fact that his work exercised such an astonishing effect on the human intellect for some 60 generations shows that it must have been an extraordinary production. We must look into the career of this wonderful man to discover wherein lay the secret of that marvelous success which made him the unchallenged instructor of the human race for such a protracted period. Unfortunately, we know very little as to the personal history of Ptolemy. He was a native of Egypt, and though it has been sometimes conjectured that he belonged to the royal families of the same name, yet there is nothing to support such a belief. The name, Ptolemy, appears to have been a common one in Egypt in those days. The time at which he lived is fixed by the fact that his first recorded observation was made in 127 AD, and his last in 151 AD. When we add that he seems to have lived in or near Alexandria, or, to use his own words, on the parallel of Alexandria, we have said everything that can be said so far as his individuality is concerned. Ptolemy is, without doubt, the greatest figure in ancient astronomy. He gathered up the wisdom of the philosophers who had preceded him. He incorporated this with the results of his own observations, and illumined it with his theories. His speculations, even when they were, as we now know, quite erroneous, had such an astonishing verisimilitude to the actual facts of nature that they commanded universal assent. Even in these modern days we not unfrequently find lovers of paradox who maintain that Ptolemy's doctrines not only seem true, but actually are true. In the absence of any accurate knowledge of the science of mechanics, philosophers in early times were forced to fall back on certain principles of more or less validity, which they derived from their imagination as to what the natural fitness of things ought to be. There was no geometrical figure so simple and so symmetrical as a circle, and as it was apparent that the heavenly bodies pursued tracks which were not straight lines, the conclusion obviously followed that their movements ought to be circular. There was no argument in favor of this notion, other than the merely imaginary reflection that circular movement, and circular movement alone, was perfect, whatever perfect may have meant. It was further believed to be impossible that the heavenly bodies could have any other movements save those which were perfect. Assuming this, it followed, in Ptolemy's opinion, and in that of those who came after him for 14 centuries, that all the tracks of the heavenly bodies were in some way or other to be reduced to circles. Ptolemy succeeded in devising a scheme by which the apparent changes that take place in the heavens could, so far as he knew them, be explained by certain combinations of circular movement. This seemed to reconcile so completely the scheme of things celestial with the geometrical instincts which pointed to the circle as the type of perfect movement, that we can hardly wonder Ptolemy's theory met with the astonishing success that attended it. We shall, therefore, set forth with sufficient detail the various steps of this famous doctrine. Ptolemy commences with laying down the undoubted truth that the shape of the earth is globular. The proofs which he gives of this fundamental fact are quite satisfactory. They are indeed the same proofs as we give today. There is, first of all, the well-known circumstance of which our books on geography remind us, that when an object is viewed at a distance across the sea, the lower part of the object appears cut off by the interposing curved mass of water. The sagacity of Ptolemy enabled him to adduce another argument, which, though not quite so obvious as that just mentioned, demonstrates the curvature of the earth in a very impressive manner to anyone who will take the trouble to understand it. Ptolemy mentions that travelers who went to the south reported that, as they did so, the appearance of the heavens at night underwent a gradual change. Stars that they were familiar with in the northern skies gradually sank lower in the heavens. The constellation of the Great Bear, which in our skies never sets during its revolution round the pole, did set and rise when a sufficient southern latitude had been attained. On the other hand, constellations new to the inhabitants of northern climes were seen to rise above the southern horizon. These circumstances would be quite incompatible with the supposition that the Earth was a flat surface. Had this been so, a little reflection will show that no such changes in the apparent movements of the stars would be the consequence of a voyage to the south. Ptolemy set forth with much insight the significance of this reasoning, and even now, with the resources of modern discoveries to help us, we can hardly improve upon his arguments. Ptolemy, like a true philosopher disclosing a new truth to the world, illustrated and enforced his subject by a variety of happy demonstrations. I must add one of them, not only on account of its striking nature, but also because it exemplifies Ptolemy's acuteness. If the earth were flat, said this ingenious reasoner, sunset must necessarily take place at the same instant, no matter in what country the observer may happen to be placed. Ptolemy, however, proved that the time of sunset did vary greatly as the observer's longitude was altered. To us, of course, this is quite obvious. Everybody knows that the hour of sunset may have been reached in Great Britain while it is still noon on the western coast of America. Ptolemy had, however, few of those sources of knowledge which are now accessible. How was he to show that the sun actually did set earlier at Alexandria than it would in a city which lay 100 miles to the west? There was no telegraph wire by which astronomers at the two places could communicate. There was no chronometer or watch which could be transported from place to place. There was not any other reliable contrivance for the keeping of time. Ptolemy's ingenuity, however, pointed out a thoroughly satisfactory method by which the times of sunset at two places could be compared. He was acquainted with the fact, which must indeed have been known from the very earliest times, that the illumination of the moon is derived entirely from the sun. He knew that an eclipse of the moon was due to the inner position of the earth which cuts off the light of the sun. It was, therefore, plain that an eclipse of the moon must be a phenomenon which would begin at the same instant from whatever part of the earth the moon could be seen at the time. Ptolemy, therefore, brought together from various quarters the local times at which different observers had recorded the beginning of a lunar eclipse. He found that the observers to the west made the time earlier and earlier the further away their stations were from Alexandria. On the other hand, the eastern observers set down the hour as later than that at which the phenomenon appeared at Alexandria. As these observers all recorded something which indeed appeared to them simultaneously, the only interpretation was that the more easterly a place the later its time. Suppose there were a number of observers along a parallel of latitude, and each noted the hour of sunset to be 6 o'clock. Then, since the eastern times are earlier than western times, 6 p.m. at one station, A, will correspond to 5 p.m. at a station B sufficiently to the west. If, therefore, it is sunset to the observer at A, the hour of sunset will not yet be reached for the observer at B. This proves conclusively that the time of sunset is not the same all over the earth. We have, however, already seen that the apparent time of sunset would be the same from all stations if the earth were flat. When Ptolemy, therefore, demonstrated that the time of sunset was not the same at various places, he showed conclusively that the earth was not flat, as the same arguments applied to all parts of the earth where Ptolemy had either been himself, or from which he could gain the necessary information. It followed that the earth, instead of being the flat plain, girdled with an illimitable ocean, as was generally supposed, must be in reality globular. This led at once to a startling consequence. It was obvious that there could be no supports of any kind by which this globe was sustained. It therefore followed that the mighty object must be simply poised in space. This is indeed an astonishing doctrine to anyone who relies on what merely seems the evidence of the senses, without giving to that evidence its due intellectual interpretation. According to our ordinary experience, the very idea of an object poised, without support in space, appears preposterous. Would it not fall? We are immediately asked, Yes. Doubtless, it could not remain poised in any way in which we try the experiment. We must, however, observe that there are no such ideas as upwards or downwards in relation to open space. To say that a body falls downwards merely means that it tries to fall as nearly as possible towards the center of the Earth. There is no one direction along which a body will tend to move in space, in preference to any other. This may be illustrated by the fact that a stone let fall at New Zealand will, in its approach towards the Earth center, be actually moving upwards as far as any locality in our hemisphere is concerned. Why, then, argued Ptolemy, may not the Earth remain poised in space? For as all directions are equally upward or equally downward, there seems no reason why the Earth should require any support. By this reasoning, he arrives at the fundamental conclusion that the Earth is a globular body freely lying in space, and surrounded above, below, and on all sides by the glittering stars of heaven. The perception of this sublime truth marks a notable epoch in the history of the gradual development of the human intellect. No doubt, other philosophers, in groping after knowledge, may have set forth certain assertions that are more or less equivalent to this fundamental truth. It is to Ptolemy we must give credit, however, not only for announcing this doctrine, but for demonstrating it by clear and logical argument. We cannot easily project our minds back to the conception of an intellectual state in which this truth was unfamiliar. It may, however, be well imagined that, to one who thought the Earth was a flat plane of indefinite extent, it would be nothing less than an intellectual convulsion for him to be forced to believe that he stood upon a spherical Earth, forming merely a particle relatively to the immense sphere of the heavens. What Ptolemy saw in the movements of the stars led him to the conclusion that they were bright points attached to the inside of a tremendous globe. The movements of this globe, which carried the stars, were only compatible with the supposition that the Earth occupied its center. The imperceptible effect produced by a change in the locality of the observer on the apparent brightness of the stars made it plain that the dimensions of the terrestrial globe must be quite insignificant in comparison with those of the celestial sphere. The Earth might, in fact, be regarded as a grain of sand while the stars lay upon a globe many yards in diameter. So tremendous was the revolution in human knowledge implied by this discovery, that we can well imagine how Ptolemy, dazzled as it were by the fame which had so justly accrued to him,